My name is Nick, and this is the instructional video for Lesson 1. Have you ever tried to draw a motion? Suppose you throw a ball in the air and took a picture of it. What would you draw onto that picture to show its motion at that very instant? Better yet, how do you visualize the forces acting on the ball in that very moment? There's a few options, but if you were to say arrows, you'd be spot on. It's a very intuitive visualization of force, and we can use it to create complex physics diagrams to help us reason through physics problems. Now, if you're trying to make a video game, it can be very useful to visualize and create diagrams of the physics operations you're implementing, like running and jumping. However, you can't simply show your beautiful diagrams of motion to the computer. It needs things in numbers. So the question is, how do you translate your diagrams into numbers? Well, you can represent your arrows, positions, and forces as vectors. Writing, drawing, and manipulating vectors is the topic of this lesson. This lesson covers the first topic of the course on vectors. After this lesson, you'll have the knowledge to start expressing physics properties and equations in terms of vectors, which will be covered in the next lesson. By the end of this lesson, you should be able to draw the visualization of a vector, write the mathematical notation of a vector, list a basic set of operations that can be used on vectors, and list what the result of each operation will give. Warning! From this point on, you will encounter math. But don't be afraid. The point of this lesson is not to make you remember every equation you encounter, but simply to build an awareness of them and their utility. You need to know what to use, but you can always Google how to use them. Now, what are vectors? They're math arrows, a mathematical construct representing direction and magnitude. Vectors are often visualized on a Cartesian plane. This is because a vector is just a container of values, one value per axis, x, y, and occasionally z if you're in 3D. You'd be right to say that the vector looks like a coordinate or a point in the plane, but it's important to understand that vectors are always pointing out from the origin. This is because a vector always points in a direction, whereas a coordinate, like x, y, is just a point on a graph. Notice how vectors are often notated with an arrow above the name. We'll cover a basic set of vector operations: addition, subtraction, scaling, the dot product, and cross product. So vectors have components, x and y. To add two vectors together, you simply add their x and y components separately. This diagram shows how vector addition, like normal addition, is symmetric, as in it doesn't matter which vector is added first. Here's an example of adding two vectors together. In the left image, you have vector A pointing from the origin to coordinate 4, 2, and vector B pointing from the origin to coordinate 1, 3. In the right image, B is added to A. You can see how B starts from the end of A instead of starting from the origin. The resulting vector points from the origin to coordinate 5, 5. The first value is the x component of A and B summed, so 4 plus 1, and the second value are the y components summed up, so 2 plus 3. Here's an example of vector addition in action. Two forces acting on this plane are interpreted as vectors. The oncoming force of the wind is added to the force of the plane's propeller, resulting in the plane's actual direction listing slightly to the right. Subtraction is very similar to addition, having you subtract the individual components from each other instead of adding them. Vectors can be scaled, as in made longer or shorter. This is done by multiplying the vector's components each by a scalar, which is just a number like 0.5 to shorten by half, or 2 to extend by a factor of 2. Now don't be scared by this equation. To be able to use more complex equations, we need to be able to calculate a vector's magnitude and direction. Here's the equation for calculating the magnitude. As you can see, when you visualize a vector as its components, it's just a triangle. Consequently, this equation is just the Pythagorean theorem, which you may recognize from high school math. Now, how do we calculate a vector's direction? A vector's direction is just the same vector, but with a magnitude of 1. We consider these vectors, which have been scaled to have a magnitude of 1, normalized. So to calculate it, you need the vector's magnitude, and you scale the vector by 1 over its magnitude. This is like dividing a number by itself to get 1. There are two ways to multiply two vectors together, either taking their dot product or their cross product. Let's start with the dot product. The dot product is useful, and is often used when calculating forces on an object. The result of the dot product A and B, written A dot B, describes how much of the vector A is going in the direction of B. Here are two ways you can calculate the dot product. I find the method on the right is simpler, as it doesn't require any trigonometric functions like the other method. However, there's a bunch of mathematical mumbo-jumbo that makes the method on the left actually make a lot of sense. I posted a video describing it on the course website. The cross product of vectors A and B gets you the vector that's at the right angle to both. There are also two ways to calculate the cross product, as shown on this slide. When programming physics, I've often found myself wanting to know the angle between two vectors, particularly when I'm calculating rotation. The dot and cross products can be used together to get the positive or negative angle between two vectors. Say we want to know how many degrees to the left or right that vector B is from vector A. Step 1. We normalize the two vectors and take the dot product. This gets you the acute angle between the two vectors. Step 2. Calculate just the z component of the cross product and get its sign by dividing it by the absolute value of itself. This gets you the direction, left or right, the vector B is from A. And step 3. Multiply the angle by the sign. That gets you the degrees to the left or right from A to B. Many programming languages, particularly ones with libraries dealing with graphics and video games, have 2D and 3D vector libraries you can utilize in your projects, which often feature all the operations we've discussed in this video. If there isn't a library you can use, or you simply want to make your own implementation, it's quite simple to implement these operations, as it can be broken down into simple arithmetic on the x and y components. To summarize, the vector is a mathematical construct that can be used to describe motion. It will allow you to easily translate your human-readable physics diagrams into computer code. This lesson video has covered the basics of vector algebra, which will allow you to better describe physics operations, properties, and systems in later lessons. Now that you've watched this lesson video, you can get started on this lesson's tasks and assignments. First, you should make a post on the introductory thread in the class forum, introducing yourself with a small paragraph describing your background in mathematics, programming, game development, and your motivation for taking the course. After that, read through the relevant articles and watch the video posted to the Moodle course page under this lesson. Then solve 4 sets of online exercise questions on the Moodle course page. And finally, take the Moodle quiz on all the content covered in this lesson. Feel free to contact me if you're having any problems or need clarification. Thank you for watching.